The year 1958 marks a watershed moment in the history of condensed matter physics, a publication of the Bardeen, Cooper, and Schrieffer theory of superconductivity, often referred to as the BCS theory. This groundbreaking work provided a microscopic explanation for the phenomenon of superconductivity, a state of matter characterized by the complete absence of electrical resistance below a critical temperature. Before BCS, superconductivity, discovered by Higgs Kamerlingh in 1911, remained a profound enigma, resisting all attempts at a comprehensive theoretical understanding. The theory not only revolutionized the field of superconductivity, also had a lasting impact on other areas of physics, including nuclear physics and particle physics. The genesis of BCS theory lies in a complex interplay of experimental observations and theoretical developments spanning several decades. Key experimental findings included the Meissner effect, the expulsion of magnetic fields from a superconductor, and the isotope effect, the dependence of the critical temperature on the isotopic mass of the constituent elements. These clues hinted at the involvement of lattice vibrations, or phonons, in the superconducting mechanism. Crucially, the theoretical groundwork involved attempts to apply quantum mechanics to the problem of electrons in solids. The independent electron approximation, which treats electrons as moving independently of each other in a periodic potential, proved inadequate to explain superconductivity. In fact, it predicted the opposite: electrons should repel each other because of their like charge. Some researchers posited that this was incorrect, and some form of attraction was occurring between electrons. A pivotal theoretical step was Cooper's 1956 discovery that electrons near the Fermi surface in a metal could form bound pairs, now known as Cooper pairs, even in the presence of a repulsive Coulomb interaction, provided there exists an attractive interaction mediated by phonons. This seemingly paradoxical result stems from the fact that the electrons near the Fermi surface are highly susceptible to small perturbations, and the attractive interaction, however weak, can overcome the Coulomb repulsion. This provided a basis to form a new ground state. The BCS theory, published in 1957 and elaborated upon in the 1958 paper, built upon Cooper's insight to construct a comprehensive microscopic theory of superconductivity. The central tenet of the theory is that superconductivity arises from the condensation of Cooper pairs into a macroscopic quantum state. These Cooper pairs, unlike single electrons, behave as bosons and can therefore occupy the same quantum state. The formation of Cooper pairs is mediated by the exchange of phonons between electrons with opposite momenta and spins near the Fermi surface. This interaction effectively creates an attractive force between the electrons, leading to the formation of a bound. The BCS theory provides a quantitative description of superconductivity, predicting a variety of observable properties with remarkable accuracy. One of the key predictions is the existence of an energy gap in the excitation spectrum of a superconductor. This energy gap represents the minimum energy required to break apart a Cooper pair and excite an electron to a higher energy state. This prediction was confirmed experimentally by tunneling experiments, which showed a sharp threshold in the current voltage characteristic of a superconductor-insulator-superconductor junction. The theory also correctly predicts the temperature dependence of the energy gap and the critical magnetic field, the field above which superconductivity is destroyed. Mathematically, the BCS theory is based on a mean field approximation, which simplifies the many-body problem of interacting electrons by replacing the interactions with an average potential. The Hamiltonian describing the system can be written as the sum of the kinetic energies of the electrons and an effective interaction term that counts for phonon-mediated attraction. The ground state of the system, the BCS ground state, is a coherent superposition of electron pairs with opposite momenta and spins. The wave function, describing the BCS ground state, is a product of factors, each representing the probability amplitude for a pair of electrons with opposite momenta and spins to be either occupied or unoccupied. The theory allows for the calculation of the energy gap, denoted by delta, which represents the binding energy of the Cooper pairs. The energy gap is given by the equation delta equals 2 times the Debye frequency times e raised to the power of -1 over n of 0 times v, where the Debye frequency represents the maximum phonon frequency, n of 0 is the density of states at the Fermi level, and v is the effective interaction strength between the electrons. The BCS theory had an immediate and profound impact on the field of superconductivity. It provided a coherent framework for understanding the existing experimental data and made numerous testable predictions that were subsequently verified. The theory also stimulated a great deal of further research, leading to the discovery of new superconductors and the development of new theoretical techniques. The ability of BCS theory to quantitatively explain the properties of conventional superconductors made it an immediate success. Beyond its direct impact on superconductivity, the BCS theory had a significant influence on other areas of physics. The concept of Cooper pairing was adapted to explain superfluidity in helium-3 an isotope of helium that exhibits superfluidity at extremely low temperatures. The BCS formalism was also used to describe the formation of correlated electron pairs in atomic nuclei, leading to a better understanding of nuclear structure. In particle physics, the Higgs mechanism, which explains the origin of mass for elementary particles, is mathematically analogous to the BCS theory of superconductivity. The Higgs field, which permeates all of space, plays a role analogous to the phonon field. Superconductor elementary particles acquire mass by interacting with the Higgs field, similar to how electrons acquire BCS. Despite its successes, the BCS theory has limitations. It applies only to conventional superconductors, materials in which the superconductivity is mediated by phonons. The theory breaks down for high-temperature superconductors, materials discovered in 1986, that exhibit superconductivity at much higher temperatures than conventional superconductors. The mechanism of superconductivity in high-temperature superconductors is still not fully understood, but it is believed to involve more complex electronic correlations than those described by the BCS theory. While a complete theory to explain these novel materials has yet to be realized, many of the fundamental ideas introduced by BCS theory have proven important in understanding these exotic states of matter. The contemporary reception of BCS theory was overwhelmingly positive. Although some initial skepticism existed, some physicists regarded the idea of electrons attracting each other through phonon exchange as counterintuitive. The remarkable success of the theory in explaining experimental results, however, quickly dispelled these doubts. Physicists were astounded by the ability of the theory to precisely predict the thermodynamic properties. Superconductors, the award of the Nobel Prize in Physics to Bardeen, Cooper, and Schrieffer in 1972 solidified the theory's place as one of the most important achievements of 20th century physics. The BCS theory has directly influenced numerous subsequent works and researchers. For instance, Philip Warren Anderson, who later won the Nobel Prize himself, further developed the theory to account for the effects of disorder in superconductors. He argued that the presence of impurities could suppress superconductivity by disrupting the Cooper pair formation. Lev Gorkov extended the BCS theory to a finite temperature using Green's function techniques, providing a powerful tool for studying the properties of superconductors at different temperatures. Walter Cohen, who developed density functional theory, a widely used method for calculating the electronic structure of materials, also drew inspiration from the BCS theory. Density functional theory treats the electronic density as the fundamental variable, similar to how the BCS theory treats the Cooper pair density as the fundamental variable. The enduring legacy of the BCS theory lies in its profound impact on our understanding of superconductivity and its influence on other areas of physics. The theory provides a powerful framework for understanding the behavior of electrons in solids and has paved the way for the development of new superconducting materials and devices. It's difficult to overstate the influence of this work. From medical imaging to high-energy physics, superconductors impact nearly every aspect of modern technology. The theory serves as a testament to the power of theoretical physics to explain complex phenomena and to inspire new discoveries. Although alternative theories have emerged, and although BCS theory only accounts for some superconductors, it is still considered one of the most significant physics achievements in the 20th century.